In some cases, when you have a differential equation, you might not end up with a homogeneous format or homogeneous functions that you can apply. For example, the method y equals to v times x. But we see linear combination between variables in that differential equation, and luckily for us, we can apply substitution method. Let's take a look at this example. Here we have dy over dx equals to y minus x minus 1 plus x minus 5 plus 2 raised to negative 1. So let's do a little bit of algebra. Do we see any repetition or similar linear combination between x and y? Dy over dx can be written as, well, here you have y minus x minus 1 plus, if I factor out negative here, I get minus y minus x plus 2 to negative 1. So as you can see, the quantity here, y minus x, the linear combination between x and y is repeated here and here. So what you can do, you can apply substitution method. You can use a variable like u, v, z, and define z to be y minus x. Then you need to find the differential of z as well. The differential of z is equal to dy minus dx. Okay, now that here you have dy over dx, so eventually you're going to replace that using this new differential. So dz divided by dx is equal to dy over dx minus dx over dx. So what we get dz dx equals to dy dx minus 1, or dy dx becomes dz dx plus 1. So the first substitution and the second substitution. We're going to use these two and then try to make this differential equation to the form that is easier for us to solve. So on the left-hand side, it becomes dz dx plus 1 equal to, well, y minus x is now z minus 1 plus negative z plus 2 raised to negative 1. Very well. So if you subtract 1 from both sides, dz dx becomes z minus 2 plus negative z plus 2 to negative 1. Or dz dx becomes z minus 2 minus 1 over z minus 2. Is this separable? Well, as you can see, you have z and the rest of the terms. On the right-hand side, there is no x involved. So of course, you can separate this differential equation. So after doing algebra, now we are dealing with a separable differential equation. We have to apply calculus, taking the integral of both sides. We have the integral of dz divided by, let me write this down here in the separable form. So then we take the integral z minus 2 minus 1 over z minus 2 equals to dx, and this guy becomes, here we have z minus 2 dz divided by, here we get z minus 2 to the second minus 1 equals to dx. So z minus 2 dz divided by z minus 2 squared minus 1 is equal to the integral of dx. Here you can use substitution method. You can say that, hey, my u is equal to z minus 2 to the second minus 1, and du is 2 z minus 2 dz. So this guy becomes, well, here we have a half, and the integral of du divided by u equals to x plus c sub y. So we get a half ln of absolute value of u, which is z minus 2 to the second power minus 1 equals to x plus c sub 1. If you multiply everything by 2, we get ln of absolute value of z minus 2 to the second minus 1 equals to 2x plus 2c sub 1. You can call this c sub 2. And here you have z minus 2 to the second minus 1 equals to plus minus e to 2x and e to c sub 2. And eventually, z minus 2 to the second minus 1 becomes e to 2x times c. Okay, guys, note that you have z in the final answer in the general solution, but your original differential equation is in x and y. So remember that you have to convert it back into x and y. So this guy becomes y minus x minus 2 to the second equals to e to 2x times c plus 1. We found the general solution for this differential equation. Can we isolate y on one side? You might say, hey, I have y minus x minus 2 equals to plus minus square root of e to 2xc plus 1, and y becomes x plus 2 plus minus square root of e to 2x times c plus 1, written in explicit form. So implicit form, implicit general solution, and this is your explicit general